Okay class, so this video is on your kinetics review. We're going to go over the answers for that review package or that review sheet, and then just going to ask some questions that will test your understanding of the material and whether you're ready or not to write the test. So that first question, how can a graph of 1 over delta T versus concentration be used to determine the order of reaction? Really the answer we're looking for is that there was a bunch of experiments conducted, and then that measures the initial concentrations of the reactant. When you graph it, they should look something like this. So 0 looks like that, first reaction, or 1 order reaction, looks like a direct relationship, and anything that's greater than first order reaction, when you put a line of best fit, it looks like a curve, it's exponential. Question number 2, what is meant by activation energy of the reaction? Pretty straightforward. Activation energy of the reaction is the minimum increase in potential energy of a system required for molecules to react. So it's really the amount of energy you need for a reaction to occur. Okay, third question. Consider decomposition of hydrogen peroxide as shown below. If the rate of decomposition of hydrogen peroxide at a particular temperature is determined to be 0.098 moles per liter second, what are the rates of reaction with respect to each of the following products? So breakdown of H2O2 will give you water and half a mole of O2. So here we're just looking for molar relationship. So if we know that the average breakdown of H2O2 is 0.098 and that's 1 mole and water is also 1 mole, then water has to be the same. Okay? It doesn't matter what we're looking at, what kind of species it is, what kind of reactants or products we have. It's a 1-to-1 relationship. It's going to be the same. For O2, because it's half a mole, or it's half of what H2O2 is, we're going to divide it by 2, so we're going to get 0.049 moles. That's all I'm looking for here. Next question. Use the following data to calculate the reaction rate law for this system. Note the rate law is the rate law expression together with the appropriate value of K. So in this one you have to solve for K also. So we have this reaction right here, so nitrogen monoxide plus hydrogen gas will give you HNO2. We have a whole bunch of trials, a whole bunch of numbers, and really you don't need all of these, you just need a few. So we know that what we're looking for here is K NO to the power of something and H2 to the power of something. We're going to solve for these variables and K. So using experiments 1 and 2, like used here, found out that if you double the concentration of NO, the rate quadruples. So you plug that in, that means 2 times something, or 2 to the power of something, equals 4. And when you solve for that, you get 2 and 2. So we know that that exponent over here is going to be a 2. And then when we look at any two experiments for H2, in this case it took 4 and 5, so when the concentration doubles, so does the rate. So we know that it's a 1-to-1 relationship. So 2 to the power of something will give you 2. So that answer is going to be 1, so we're going to say that this is 1 right here. So this is our new rate. Rate equals K NO squared and H2 to the power of 1. Now we have to solve for the value of K. So here we use experiment 1 data, using the rate law, fill in the values from data table. Okay, so we say that the rate was 0.002 moles per liter per second in experiment number 1. We sub in the appropriate values for NO and for H2 from experiment number 1. We put the exponent, so that's 2, and exponent here is 1, and we just isolate and solve for K. We find here that K is this value right here, which is, when you do the calculations on your calculator, it should come out to about 500,000 seconds per molar squared per liter squared. Just be mindful of the units when you're doing these things, okay? If you write it out, you should be able to cancel out and add units wherever possible. So rate law for this one is rate equals value of K, and remember this -2 means that these are on the bottom. So if you had another way to write this, it would be seconds per molar squared, so positive squared, and liter squared. And we put NO, moles per liter, so because that's the concentration, we put squared, and here it's to the power of 1, so you don't have to put anything. This is a pretty straightforward question. It just requires you to just follow the data, make sure the numbers are right. Don't mess up your units. Next question. Chemical reaction between X and Y is known to be first order, so that's a big hint. For each reactant, find the unknown information in the table below. So here really we're looking to find K first, and then we can find everything else. So here we have our rate equation. They're both to the power of 1. So therefore we just solve for K. So here we know from our first data table, first row of data which is complete, K is equal to, rate is equal to 0.2. and then we can just sub in these values right here, solve for K. If we solve for K, then we can find out what A is, and we can find out what B is. Really, you're just using the same equation again, you're just looking for a different variable this time. At high temperatures, the following reaction occurs. So this is ammonia reacting with oxygen gas. You get nitrogen monoxide and H2O. Show the concentration of ammonia of 0.12 at 10 seconds, and then 45 seconds later, at 55 seconds, we had concentration of 0.1, so it decreased. Calculate the average rate over this time interval. So average rate is pretty straightforward. You're just looking at final minus initial, so we have 0.1 minus 0.12. Our final time, which is 55, minus our initial time, which is 10. Negative sign just means it's being consumed. So NH3 is being consumed to make product over here. So we find out that it's being consumed at a rate of 4.4 times 10 to the negative 4 moles per liter second. Second question was, what's the rate of production of water? So if this is being consumed, then water has to be produced because that's a product. We take the same rates that we had for ammonia, and then we just multiply it by whatever the molar ratio is. So here we have 6 to 4, which is 3 over 2 in simplified terms. You multiply by 3, divide by 2, that's your rate right there. Rate of production of NO, here it's a 1-to-1 relationship because this is 4, this is also 4 moles, so you just do in simple terms 1 over 1, you should get the same answer. Rate of consumption of oxygen, here it's a bit tricky just because the numbers are messed up, so you have 5 and 4, but really nothing too difficult. You use the same rate that you started with, times by 5 over 4, and this means 5.5 times 10 to the negative 4 moles per liter second are being consumed. Okay, so this much oxygen is being consumed per second. Okay, following results were obtained when the reaction represented below was studied at 25 degrees Celsius. So here's our equation, and then here is our data table. So write the rate law expression for the above reaction. First, what they did is just they found out what those exponents were. This should be pretty straightforward. There's nothing difficult about this. To write the rate law, here we go. So we just took rate 2 divided by rate 1. Solve for that, and m is equal to 1. Same thing over here. They did rate 3 and rate 1 just based on the exponent here, and we solve for that. They're both to the power of 1. Again, you're just looking at two things which are different. So if you're trying to solve for ClO2 and use these two right here, that wouldn't get you anywhere because these are the same values. You need to use two values which are different. So for ClO2, what they did was they used 3 and 1. Okay. And that's your rate law. So the answer is pretty straightforward here. They didn't ask to solve for K. Over here, you're solving for K. So you know what this is. You're given these values in table. You can substitute any ones. It doesn't matter. So they took from trial 1. Both of the values were, this was ClO2 was 0.01, F2 was 0.1. You're given the rate also. So that's R. You're solving for K. Just watch your units. This one came out to 2.4 right there. And here we have question number C. In experiment 2, what was the initial rate of decrease of F2? So you just take the rate that was given, and then you just multiply by the molar ratio. So here we have the rate of this is 9.6, and they're asking what's the rate of decrease. So you have 2 moles here, you have 1 mole here, you're just going to divide by 2, so it's just pretty much half of it. That's what your rate is. And finally, which of the following reaction mechanisms is consistent with the rate law developed in A? So like I said before, reaction mechanisms, they're just guesses, right? And they're highly educated guesses. So as long as a reaction mechanism works or it makes logical sense, we can use that as a correct mechanism. So here we have 2 proposed mechanisms, and we're just trying to figure out which one is consistent with our rate law, which is this right here. So which one fits that right there? So here we're from step 1, we take this, and then we're just dividing rates here. From step 2, rate determining step, and then substituting from step 1, overall rate right there is consistent with mechanism 1. So we're seeing that this one is the correct one right here. And the reason that we can use that is because it fits pretty much when you do the math. This one here, this one wouldn't work because you only have one reactant. And your overall rate has to have 2 reactants because that's what we figured out. And this is just in case some of the students missed this on Friday or today. If you're not told the rate equation, like the previous question, then you can use the rate determining step to figure out your rate law. So if we say that this is your rate determining step, so you have something like, let's say x is O2 and y is H2, the coefficients, the molar coefficients in front of these can be these exponents right here in the rate law, as long as what you're using is the rate determining step. So this one right here, this equation right here, has to be your slowest step, your rate determining step. You can use those coefficients as those exponents that will give you the right rate law. And then here finally for your theory and application, just a few things. If you can't answer these questions, then it is something that you should go over. Do you know how to calculate average rate? Again, this is just final minus initial, but go over it if you don't, if you can't understand it. To find instantaneous, you won't be asked any calculations, but you may be asked, like let's say at this particular point, how do I find the instantaneous rate of reaction? You would just say at this point, there would be a tangent, and that would be good enough. Do you know what a rate determining step is? What its applications are? That's a big question. Difference between intermediates and catalysts, again, they're very similar. It's just where they're placed in the reaction that makes them different. Do you know what activation energy is? And that's a bit different from threshold energy, so be mindful of that. What constitutes an effective and ineffective collision? This we covered quite a bit. Effective collisions, they require particles or molecules to come together, and they have to be successful. They have to reach a certain threshold of energy. They have to have carry a certain amount of kinetic energy for it to be successful. What a reaction mechanism is and how it works. Again, this was pretty big stuff. You should be able to manipulate reaction mechanisms, find out what the rate determining step is, or if you're given 2 elementary equations, find out the third one to give you the overall. What's an activated complex? And finally, what's temperature? Again, this is from the last chapter. It should be pretty clear now what temperature is. Best of luck tomorrow.